Hi, I'm Ryan Rayshak. I built the embedded system for the onboard exoskeleton. Let's get into it.
So what is an exoskeleton? An exoskeleton is a suit that is designed to assist the user in some application. There are currently many designs that exist, such as the DARPA exosuit that is being designed to carry more weight for soldiers, or even the Spartan suit in the iconic video game Halo that helps soldiers not only be stronger, but protect them from incoming bullets. There are even exoskeletons for paraplegics to help with walking, and some in the works for helping workers carry heavier weights or heavier tools. The exoskeleton we are looking at today is the Minds Robotics exoskeleton team's. The Minds exoskeleton team is designing one that helps with lifting more weight while not impeding walking or even running. This exoskeleton, due to its complexity, needs an embedded system which can convert forces applied to a leg and translate that into a motor movement. Seen here is a basic layout of the system. To turn on the exoskeleton, a battery must be connected, followed by a user toggling a switch. Once power is on, the user can apply force on a or both desired legs to get movement. The force will be translated into weight by a load cell, which will convert that force into an analog signal, which later will be translated by an analog to digital converter and be processed by a microcontroller to determine the direction and speed of the motor. Our microcontroller is a PIC18F26K22. The computation will then be sent to a motor controller, which will tell the respective motor what to do. To tweak system performance and adjustability, the user can press keys on a keypad. Let's now see a demonstration of the system working. For this demo, one leg will be shown to be operational.
Go. Okay, so how we power on the exoskeleton is we get the. This is the electronics box. Right now it's not fully fixed, but that's okay. We'll then clip it into the battery box, which houses the battery and keeps it nice and connected. All right, if you can see over here, the battery box is turned on and ready to go, and it's not yet ready for the user to go on until I hit this switch, and there you go. We have power to the exoskeleton. So next, you strap yourself in. All right, and then once you strap yourself in, you should also put on your handy dandy controller. With your controller, you can control three things: reactivity, tension of the cable, and third, you can control the range of that tension that it tries to remain within. So, reactivity is controlled through 1 and 4. It's a little bit unnoticeable. You can control it through maybe some of the extremes, but it's not very good. 2 and 5 is very useful for the tension. Well, I'm going to show you that right now. So I'm going to increase it. There you go. You can see it kind of try to increase it, and I even feel it a little bit too. All right, I'm going to decrease it back because I don't really like that. See, now it's nice. All right, I'm going to go to 3 and 6, which is the delta, or the range of values that are acceptable tensions. Mainly, it means it's a slightly more like stiff, which may be very useful for certain situations. Because right now, I can only go one direction. That's actually could be useful. However, though, maybe I want to have it not be stiff, and that's actually very perfect for this very good situation. All right, now you strap yourself out, and you should be good pound down the exoskeleton on your own.
Here's what actually was going on inside the embedded system. Turning on the exoskeleton, there are mechanical switches that connect the battery to the battery box. This battery turns on the motor controller. The motor controller has a built-in 5-volt converter, which is connected to an electrical switch, and a USB converter that is fed into the PIC, which powers the rest of the systems. Now, starting from the left side of the block diagram, the forces applied to the leg is translated by a load cell into an analog voltage, which is then processed by an HX711 load cell amplifier. It's a 24-bit ADC that has adjustable gain and has built-in first-order low-pass filter to help read the load cell with ease. This will be discussed more in depth later on as a crucial subsystem. The ADC value is stored in a register and later read by the PIC. The PIC then translates the signal by looking at the most significant bits and compares it to the stored tension value that can be adjusted using the keypad. Once it is processed, a direction based on the difference between the obtained tension and desired tension, it uses serial communication to the motor controller to tell which motor wants to move, what direction, and what speed that motor that it should be performing. Then it goes into a feedback loop trying to obtain a close enough tension to the desired one. The keypad exists to help, as stated, adjust the speed of reaction, desired tension, and range of values that is close enough to the desired tension. How the keypad works will also be discussed more in depth. The HX711 is probably the most useful and interesting part of the entire system. This part is really easy to work with once you fully understand it and is fairly well documented even on the board itself. The ports to the left are colors commonly associated with the load cell. VDD is a voltage in the logic/upper voltage of the ADC of the HX711 chip itself, and the VCC is a power to the load cell. These are tied together for our purposes. DAT, short for data, is the output of the chip, which is obtained using a clock signal to the right. How it works is data, or D-out, is a logic high when the ADC is processing the input and is low when it's ready to send the bits in the register. Then a clock signal is given and it must be high for no more than 50 microseconds or else the chip will restart at 60 microseconds. It can be logic low for as long as you want. Because of this timing, a timer ISR on the PIC wasn't helpful or even fast enough to obtain the bits needed without accidentally resetting the chip. Instead, a simple for loop did the trick. The clock signals have the data first give the most significant bit and then least significant bit, but the number of pulses determine the gain. For instance, a gain of 128 is done with 25 pulses, and a gain of 26 is 27 pulses. There is another channel that isn't used but could be used to have a gain of 32 with 26 pulses. The ADC with the HX711 is 24 bits, but the value is in 2's complement, meaning that it can represent negative and positive values. Testing found that it was negative when it wasn't being touched or was being pushed down, but was positive when it was being pulled. Obtaining the bits wasn't a challenge, but understanding them and getting the PIC to work with them was a totally different story. For future reference, when using the PIC, a 32-bit unsigned integer actually sign extends at the 16th bit, meaning that once the 16th bit is stored in a 32-bit unsigned integer, the most significant 8 bits are lost to whatever bit that happened to be. This was fixed by putting the most significant bits into a 16-bit unsigned integer. The keypad made this embedded system not only more interactive but easier to test. How the keypad works is that it's a matrix that needs to be separately written a logic high or low to the rows, which are 8, 7, 6, and 5. The columns then need to be digitally read from which are ports 4, 3, 2, and 1. The code shows this more clearly. The data sheet wasn't much more helpful than that, as it required lots of experimentation to get working, mainly because this was expected to be paired with an Arduino. This system required by far the most tweaking due to timing issues and the balance of keys, meaning sometimes a left adjusted key was read to be high when it really wasn't being pushed. Even when it was working on its own, it needed to be adjusted with the full suit working.